Now that we've had some practice working in polar coordinates, working in situations where our distance from the origin, our radius r, is a function of the angle that we're looking in, our theta, we're ready to start doing calculus again. So let's start off with a simple example. I've got a circle of radius 1, so my r is a function of theta. It's just a constant function. And I want to find the area of this circle. My independent variable is theta. So when I go to integrate, I'm going to be integrating with respect to the variable theta. It'll be some integral of a function d theta. But the integral formula that I use will be different than before. So when we learned about integrals way back in Calculus 1, we start off with this idea approximating an area using rectangles. And that makes sense because that is an easy way to measure area, at least for situations where the y coordinate is a function of the x coordinate. But that idea is not as helpful in polar coordinates. So the reason I've chosen a circle here to start out with is to help illustrate an easier way for finding area underneath polar curves. So let's say that I've got some range of theta values, some range of angles that I care about. So maybe I'm looking for all the possible angles between 0 and, let's say, pi over 6, right? So I've taken some piece of the possible angles. So in this case, it would be some piece of the unit circle. Pi over 6 would be about this much. And I can look at all the possible values of r. Let's say r from 0 up to r equals 1. And I picked r equals 1 because that's the function that I care about here. And I can fill in this area of the sector of the circle. Just a fancy name for this wedge here. And I want to calculate the area of this thing. So I know that this is a certain fraction of the whole unit circle. How much of it is there? This is 1/12 of the unit circle. So I know that my area in this example, well, I've got 2 times pi for the whole, excuse me, not 2 times pi. I've got the area of the full circle is pi r squared, but my r is 1, and I need to divide by 12. So this should be pi twelfths of a unit of area. But in general, right, my r can be some different number. How do I account for the theta here? Well, this number here, pi divided by 12, this is exactly 1/2 of the angle that I've got, right? So this angle from here to here is exactly pi over 6 radians. My area formula, I've got 1/2 of that. So this is really important that my area is always going to be r squared times theta divided by 2. Now, for more complicated functions, let's say I've got r is not equal to 1. Let's have a more complicated function here. Let's say this is 1 plus sine of theta. I get a different looking curve. This is called a cardioid because it kind of looks like a heart. So it's upside down the way that I've graphed it here. How would I find the area of this thing? So this curve consists of all the points where the radius r equals 1 plus sine of theta. And the idea I'm going to have is I'm going to break this down into those sectors, those wedges, right? So I'll go out a ways. I'll have some small change in my theta, which actually gives me quite a large area the farther I go out. The length here of this radius is still just r as governed by this formula. But what I'm going to do, because I have integrals in mind, is I'm going to call the angle here, this is really the change in my theta. So this is my my delta theta. So what amount of area am I adding up? I'll have a certain number of sectors depending on how many pieces I'm breaking this down into. And I need to add up my area for each piece. The area is again r squared times my angle, which is now delta theta, all divided by 2. And let's say that I have n of these sectors that I'm all adding them all up in. Like here and here and here and so on. Well, this calculation, what is my r here? My r is a function of theta. So really, this is f of theta, whatever my function is. For this example, it's 1 plus sine of theta. And I have to square this and divide by 2. And then I've got my delta theta. Now, I'll have different sample points, of course. I'll have like theta 1, theta 2, theta 3, and so on for each one of the sectors that makes up my approximate area, right? These will still be a little bit too small in places, a little bit too big in others. And I turn this into an integral by taking the limit as n goes to infinity, right? So any finite sum here is only going to be an approximation of my area that I want. To find the true value, I have to take the limit of those approximations. And here I've got, here's my formula. Here's my delta theta. So this looks a lot like the limit of a Riemann sum. So I should be integrating, let's say, from theta equals A up to theta equals B. We'll figure out those numbers in just a minute here. But I'm integrating the function f of theta all squared, then divided by 2 d theta. That's the integral formula for finding the area enclosed by a polar curve. Now, the start and stop points that we use here will measure what are the possible angles that I'm using, right? So if I start my integral, let me clean this up a little bit. If I start my integral at theta equals 0, I'm starting at the positive x-axis. And then depending on where I stop my integration, I will be filling in more of the curve, more of the cardioid in this example. So this orange region that I've colored in, I could measure this amount of area by calculating the integral. In Desmos, I just have to write the letters I and t, and it knows that I want an integral. I'll start my lower bound at theta equals 0. My upper bound, it looks like I've gone all the way up to an angle of pi over 2. So this is all of the area enclosed by the cardioid in the first quadrant. Now the function that I use is going to be 1 plus sine of theta. I need to square this, divide by 2, and again, my differential here is d theta. Desmos calculates this integral for me, and I get a number slightly bigger than 2.